Here's force on a curved wire. All right, so now instead of a straight wire, let's have a very curvy wire. And let me try to draw it nicely. It has a uniform diameter. Like that. Oh, so close. Okay. And there's current flowing through this wire. The same current has to flow all the way through the wire, like that. And let's put it in a magnetic field. Doesn't have to be uniform, but I'll draw it uniform just to make it easier to see. All right. If this wire were straight, we would have F on the wire equals IL cross B, like we just talked about. If it were a straight segment, current gives you the direction, the length of the straight segment gives you the magnitude of L. We don't have that. We have a curved wire. So what we have to do is break it into little pieces, right? So if it's curved, and if we look at a small enough piece, like this piece right here, that piece is essentially straight. So this is a differential segment of the wire. And when you hear differential, you know what's coming. We're going to do an integral. But first, let's think about the force on that differential segment that we call ds. Okay? So let's look at a segment of the wire. Well, since it's a little piece, we're just going to figure out a little piece of the force, dF. dF is the differential force on this little segment, ds. Well, let's just copy the equation. I, the current, is the same everywhere. So for L, that's the size and the direction of the current. So we actually call our ds a vector. We draw a little vector like that, ds. And if we were to draw it here, there's ds. And if we were to draw it here, there's ds. So ds just marches along the wire, following the direction of the wire and the current, and always a little differential small piece, so it looks straight. So I ds cross with B, whatever the B field happens to be, wherever you are. Okay? So pretty much the same thing. We just replaced L with ds. So now we just have to integrate. We add up the force on all these little ds's. And you could worry, what if it curves and the force is in the opposite direction? That's okay, because it's a vector. We're adding up all the vector df's. So let's say for a curved wire, then we just integrate to get the total force, FB, and it would be the integral of I ds cross B, and we have to say from where to where. Well, we could sort of start here and go here. If we want to do the whole thing, we could go from A to B. So that's just, those limits are where you follow, from what point on the wire to what other point on the wire. So when you integrate along a line like that, it's called a line integral. It has several other names: contour integral, line integral, whatever you want to call it. And it looks pretty tricky to do this integral, because here's your ds, here's your differential in your integral, and it's a vector, and it's crossed with something else, right? This is vector calculus. It gets pretty ugly. You have to cross your ds with your b to get its contribution to df, and then add them all up, and it's a mess. That's why vector calculus is hard. Just like the vector flux for Gauss's law, though, we're always going to do fairly simple geometries where it won't be that hard to figure out the integral without having to actually do the integral.